Okay. All right. So last time we started the idea of the Fourier transform. All right. So it's closely linked. It gets confusing. We did a Fourier series, and there is a Fourier transform. The Fourier transform. Somebody asked last time. They've heard of the Laplace transform. You did that in differential equations. Laplace transform, Fourier transform. They're very closely related to each other. I'm not going to get into the real connection between the two, but there is a connection between the two. All right. My focus really is much more introducing these concepts to you guys and preparing you for stuff that you're going to do in junior year and 3111, 3112 to use this stuff, and also into DSP. Okay. So wake up. All right. So last time I introduced the idea of the Fourier transform, and actually, this is something that you've been using. So impedance analysis really is kind of a special case that is the Fourier transform, as it turns out. And I introduced this idea last time. I showed my phone where I had this app where I had this sound analysis oscilloscope thing, and I had the spectrum analyzer thing. So I guess maybe I'll do that again, because I do think this is an important concept. So where's my oscilloscope thing? Here it is. Okay. So let's see, if I put that back up there, I guess it doesn't want to turn. Okay. This is what I would call a time domain signal. I don't know how well you guys actually see that there, but what you see is a waveform jumping up and down. That's a voltage. So basically the microphone here outputs a voltage signal, and that voltage signal is what's seen on the oscilloscope. This is what I would call a time domain signal. It's what we have in the real world, right? In the real world, if you measure a voltage, that voltage changes over time. Okay. So this axis here is here. Okay. This axis is time. And this would be vertically a voltage or a current. But for this particular signal, this should be a voltage. Okay. All right, that is a signal that exists in the real world. It's an ugly signal. It's a very ugly signal, right? Because why do I say it's ugly? Right? This is not even though this is a real waveform, right? That is a voltage. That does not look like a voltage they ever give you to analyze in 2112, right? In 2112, what do your voltages look like? Sinusoids, right? Now this guy is sinusoids. He's a sum of sinusoids. Right? That's the difference, right? So I can use impedance analysis, I use those concepts if I can break this guy up into his individual components. All right, so that requires my ability to look at things in what I call the frequency domain. So the other tool that I showed last time is I said, okay, well, I've got this guy here, the spectrum analyzer, which is giving me this picture. All right. This is not the real world. This is basically a computer processing something. In other words, what I'm doing is I'm taking that voltage, feeding that voltage into some sort of math that has been coded, okay, that is telling me at what frequency I have information in the waveform, right? That's basically what this picture is. So I showed it last time here, right? This is the picture we end up with. This is the output of my spectrum analyzer. So in this case, it was telling me, it looks like I've got something here, I said at 412 hertz. And then it looks like there's harmonics at that, okay? And so one place you would use this, maybe for instance, I don't want to look at myself the whole time, okay, voice recognition algorithms, right? So I could take the spectrum analyzer. So I could take a real voltage. So imagine where this would be used like in an embedded systems context, if you're an embedded systems person, right? What you would have is you would take a voltage from a sensor. In this case, that sensor is a microphone. I'd put that into an analog to digital converter. I'd have some algorithms that looked at that frequency spectrum, and then I could apply various different algorithms, right, to say, okay, well, I'm recognizing different sort of parts of speech or something in that. Okay, so the idea of being able to go from the time domain. So this is our real world stuff in the time domain to what we call the frequency domain is important, and you've been doing it for a while. This is what a frequency domain would look like. The difference here is the x-axis, right? The x-axis of this thing is t. The x-axis of this guy is omega or f, right? That's the big difference between the two. All right. Now, and I say this is not the real world. when I say this is the real world, this picture here, and this one is not, what do I mean by that? What do you think I mean by that? To say this is a real world signal and this one is not. Yeah, this is something that came from an analytical process, right? This guy right here, this waveform is the waveform that exists in the real world. Look at a sound wave. If I speak, the air is moving, all right? And I can turn that motion into a voltage. That is a real world thing that exists. Whereas telling me what frequencies are in that, I had to apply some math to that. This guy only exists in a computer. That sound wave exists in reality in time, right? It fluctuates in time. But this does not. This had to be created by a computer or some external tool to do this. Okay, that's the difference that I mean. So we tried to sort of explain this last time to say, okay, if I think of my real world stuff, there is this connection between the time and the frequency domain. So here I have this would be a real signal. And in this particular case, this signal can be decomposed into, as I've shown here, basically 3 different sine waves that have frequencies that are harmonically related to each other. And what I have, if I look at the frequency domain, basically these guys are impulses here. All right, so in this case, what looks like I've got something at F naught or omega naught, right? And then this guy, let's say, is 2F naught, and this guy is 3F naught. Okay, so if I wanted to make a function that represented this thing right here, so this real signal is x of t. All right, so x of t is made up of apparently, I'll call it this, c1 cosine 2 pi f naught t plus c2 cosine. What would I say for that guy? What would the next one be? Be 2 times that, right? So 4 pi f naught t. And then some other one would be c3 cosine 6 pi f naught t. And there might be a phase shift. I'm neglecting, but the basic idea is that those waveforms are harmonically related to each other. So what is this thing here in the frequency domain? My axis is frequency. So how would I describe this guy? I called this guy last time x of omega. Okay. And how would I write that in this particular case? How would I express? So basically, what does this guy look like he has? It's got some, turns out he's got this stuff down here, which I'm not going to get into. It's noise, right? But what is this stuff right here? What are these 3 things? So I'm making a graph of what I have in the frequency domain. So frequency is my x-axis here. So what did I say I had in this frequency domain? I have impulses, right? So I have impulses at the locations where I've got stuff. So what I ended up saying is in this case, I'm going to have something at alpha 1. I guess I'll do it this way. Alpha 1, and this would be at the fundamental. So I'd say omega minus 2 pi f naught plus his friend at the negative frequency. Plus there'd be whatever's at the second harmonic. So that'd be omega minus 4 pi f naught plus an alpha minus 2 omega minus 6 pi f naught. In other words, I get impulses. And what I said was those impulses tell me the frequencies at which I have information in the signal, right? This signal, this real signal x of t that exists in the real world only has information at certain frequencies. And this idea of the frequency domain analysis is basically trying to tell me what information I have at those frequencies. And what I kind of said, this is sort of like a compression, right? Because if you think about that real signal x of t, Between 0 seconds and 1 second, there's infinite data that's stored in x of t, because t is a real variable. But I don't need all that stuff. If I wanted to reconstruct x of t, all I really need to know is the amplitude, the frequency, and the phase, right? So if I can track that information, I can make my analysis a heck of a lot easier, right? That's the whole idea of this sort of notion of being able to have a frequency domain, is it simplifies a lot of analysis for me. Okay, so so basically, just want to make sure that we keep straight, because we're using this Fourier thing now in two ways. One is Fourier series and one is Fourier transforms. And I am only teaching you a subset of all the many things you can do with the Fourier transform. All right. So the Fourier series is a way to represent a periodic waveform, any periodic waveform, as a sum of cosines, sines, cosines, or complex exponentials. Right. Basically, harmonically related signals add together to create any periodic waveform. And the way that we learn basically three forms of that. And this is the way that I'm going to use it going forward, this complex exponential. So if I have n harmonics, capital N harmonics in my waveform, how many terms do I have in this series right here? So let's say for this guy right here, so I had 3 harmonics. So if I had 3 harmonics, how many terms do I have in this complex version of the series? Complex version of the series will have how many terms? So 3 cosines means how many complex exponentials? 6, right? One at omega naught and one at negative omega naught, right? One at 2 omega naught, one at negative 2 omega naught, one at 3 and one at negative 3. All right. So that's an important thing to bear in mind. Now, the Fourier series is basically to say in the time domain, I can think of that thing that way. The Fourier, and so notice that, so my Fourier series still represents x of t. It is a variable, is a function of time. What we said last time is x of omega. This is a function of omega. It's a function of frequency. And in particular, I said this was a complex function of the real variable frequency. To say that this is a complex function, what does it mean about every value of x? If it's a complex function, well, it means that every entry for every value of omega, the x that I get is a complex number. So can I draw that in a graph easily? If I wanted to draw x of omega versus omega, can I do that? If x is a complex number, can you draw that graph? No. What do I have to draw instead? Magnitude and angle. I gotta draw 2 graphs to be able to visualize that. And technically, I guess you draw a real and imaginary part graph, but that's not usually that useful. The magnitude and angle piece is usually a lot more useful to us. Okay. So this guy is complex. Now, what this says, and this is important, all waveforms, and I should probably be careful that there are some caveats to it. All useful waveforms, I guess I would say, maybe not useful. Most waveforms, whether they're periodic or aperiodic, can be viewed in either the time domain or the frequency domain. Now, we are going to focus solely on the ones that are periodic, okay? We're not going to get into aperiodic stuff. So for instance, if I had e to the negative at u of t, a very common signal, that has a Fourier transform, all right? I'm not going to get into what that Fourier transform is. It's not hard to figure it out. There's an equation for it. All right, but we're not gonna deal with that. You'll learn about that more in 3111. Okay. Here I want to introduce the concept. For periodic waveforms, I want to be able to view it in the frequency domain. Now you've done this before. Okay. If I give you an RC circuit, okay, this is the real world over here. This is the time domain. There is a voltage source that I hook up to this thing and I get a voltage across that capacitor. In the frequency domain, what do I have? Well, I would replace Vn with Vn's Fourier transform. and I would replace V out with V out's Fourier transform. Okay. And it turns out that if I'm in the time domain, right, this guy's going to end up being, if I do KVL, V in of t is equal to RC dV out dt plus V out is what I'm going to end up with. Over here, what would I end up with? Well, if I told you you didn't know anything about Fourier transforms, right? What would you end up with over here? How would you have done this? You've been doing it in the frequency domain in 2112. What do you do instead of writing the differential equation? Impedance. Frequency domain and impedance are effectively the same thing, right? Well, in the case of what you guys did in 2112 is you basically said that I took this voltage source, so V in, let's say, the example I'm going to end up using here, 3 cosine 2 pi t minus 30 degrees. So let's say this guy was 3 cosine 2 pi t, what did I say, minus 30? Minus 30 degrees. Okay. What would I represent V in the frequency domain, in the impedance domain, as you guys have learned it? How would I represent that here? Yeah, this guy would be 3e to the negative j 30 degrees. Right? I represent this using what I've kind of termed approach 4. I've captured this thing here called the phasor, which I pulled out of it. Okay. All right. And then V out, I don't know what that is. I would say V out has got some magnitude and it's got some angle. And how do I relate those? Well, I use impedance. And so what I would find is that V out of omega is equal to V in of omega. And if I did my work on that, I'd see it's times 1 over j omega RC plus 1, like that. Okay. This is in other words, this doesn't exist here in the real world, right? You don't measure, there's no phasors. You don't go in the lab and measure a phasor, right? And in the labs, I don't know what you guys are measuring, but you're not measuring phasors. You're looking at an oscilloscope, maybe you're looking at a multimeter, right? But you're not measuring a phasor per se, although we do our analysis over here. So technically you've been doing this. Actually, this here is really a Fourier transform. All right, you've actually been using it up until now, right? We're just trying to put some sense around it. So what we talked about last time is I tried to represent this guy in the frequency domain. All right, and let me jump ahead to the connection that we made. Basically, what we said was, if I have this periodic waveform, I put it into this form of the two complex rotating vectors. And then I can relate those complex rotating vectors to the locations where I've got frequencies there. All right, so basically trying to use that definition, I'm gonna go back here. So if I had, let's say this was my input to that circuit, 3 cosine 2 pi t minus 30 degrees. Okay, this is my, what we called approach number 1, what I've called approach number 1 to expressing this. All right, I want to put this into this third approach here, the two rotating vectors. So how do I express this V in of t in that way? So if I gave you this, how do I turn that into this form? How would I express that? There's two exponentials, right? So one of them has e to the j 2 pi t, and the other one has e to the negative j 2 pi t. What are the amplitudes on those two terms? What is it? Well, 3 over 2, 3 halves, right? Technically, it's a complex amplitude, so it's 3 halves, and what do I put in front of this? Times e to the what? Negative j 30. Okay, and then this guy would be 3 halves e to the j 30, the complex conjugate of that. Okay. Now, what we said last time is I turn this into the Fourier transform. Okay. Now, at what frequencies is there information in that signal? What are the two frequencies that have information here? Yeah, 2 pi, and what's the other one? Negative 2 pi, right? So what I would say is I have delta of omega minus 2 pi plus a delta of omega plus 2 pi. All right, those are two impulses, right? Which of those two impulses, the one on the left or the one on the right, which one corresponds to omega equal to 2 pi? This one or this one? Which one corresponds to omega equal to 2 pi?
This one.
The first one. That's right. The first one, right? So we've learned our shifts, right? This is a shift to the right, the first one. So the coefficient on that guy is the 3/2 e to the minus j 30 degrees. So this term mapped to this term. And this guy is 3/2 e to the j 30 degrees, like that. Okay. And what we said last time is then this would require two different graphs to express, right? So this guy would be, I'd put the magnitude of Vn of omega. And then over here, I'd have the angle of Vn of omega. Okay. And I would have impulses for both of those two things. So in this case, so for the magnitude, what would I sketch for the magnitude here of this thing? Be two impulses, right? Where would I put those impulses and what are their areas? Yeah, 3/2 at 2 pi. So let's call this 2 pi. This guy would be 3/2. And then he's got his best friend here at negative 2 pi over here. The two of those go together like that. And then if I look at the angle, right, over here at 2 pi, I'd have another impulse. What would my impulse be at 2 pi? What would I show for that? Negative 30 degrees. All right, and then this guy at negative 2 pi, since they're conjugates, this guy will be 30 degrees. Right, so they're conjugates of each other. That was basically what we walked through last time. Right, so in other words, I can take a waveform and do it like that. Now, what you've been doing when you did impedance is you basically were using this idea. All right, and so what the frequency domain approach, the impedance analysis approach, has been using the Fourier transform. All right, and so when I look at this, what you've been doing all along is you converted the circuit into the frequency domain. Okay, so the approach that you've been using is this idea of the phasor, which I say uses my approach number 4, where you basically took this piece right here. All right, you could also use this approach number 3. What's the difference? Well, the only difference is the magnitudes of these guys is half of what the magnitude of this is. All right, it seems like it's more confusion than it probably needs to be for you guys when you're learning this, but I didn't make up the rules. Okay, so basically what you do is you convert into the frequency domain. You use those approaches to get basically these alphas or this c times e to the j theta. You develop the transfer function using impedance. Now this is a new term I've defined here called transfer function. I'm going to talk about that in some more detail very end of class today and on Wednesday. All right. Then what I do is I figure out the output phasors, and then I go back to the time domain. So basically, you've been doing that all this time. Is if I gave you a circuit, right? The circuit exists in the time domain. I move it to the frequency domain to do analysis. I get some phasor, and then I shoot that phasor back into the time domain. Right, that's been the approach that you do because again, the real world is in the time domain. Analysis is easier in the frequency domain. All right, I think it's important that you understand that basic idea. All right. So what we learned last time was basically just like this for sort of a simple example. All right, where I think we had 3 terms in the series that I had last time. And I looked at how to make these 2 graphs, and we looked at how to plot them in MATLAB. All right, we're going to review that again today. All right, for a more complicated waveform. So again, what we talked about was basically, and this is just like what you have. If you look at what's on the homework right now, right, on homework 8, the first 2 problems, I think, on homework 8 are basically computing alpha ends. So I give you a time domain waveform, okay? And what you guys do is you take that time domain waveform and you determine the alpha values, okay? Then what you then have to do in the later problems is you have to then figure out x of omega, all right? And you have to figure out how to get to the x of omega from the alpha values. All right, now, so far, all this is just an analytical process. This is a plug and chug process. And the steps are the 3 steps that I've got right there, right? So basically what I do, if I want to get to the Fourier transform of periodic waveform, I figure out the Fourier series coefficients. I map those to the appropriate frequencies. And then I determine x of omega as this series of impulses and make the plots. Always 2 plots, one for magnitude, one for angle. All right, now again, that is just like a plug and chug process. What we're going to look at the very end of homework 8, and really we're going to focus on a lot in the project, is if I can move things into the frequency domain, it becomes easy for me to do some design. All right, there's some key design questions. We'll look at that in a little bit more detail at the very end today. Okay. All right. So let's take a look at what that looks like then in the context of what you guys are trying to figure out on the homework right now. So if I look at if I have a square wave like this, so there's all kinds of square waves, right? They can look different. This square wave is one that is 1 from 0 to t over 2. All right. And then it's -1 from t over 2 to t. Okay. And what I want to do is I want to go through these steps. So I define the steps, figure out the Fourier series coefficients, map those to frequencies, and then determine x of omega. Okay. And I've said that my period here, t equals 3. All right. Because I'm going to need that because I'm going to put this into MATLAB to make a graph of it. All right. So I don't want to, I like keeping stuff in terms of variables rather than numbers. So I'm going to keep it in terms of variables first. So help me out. How do I compute alpha n here for that waveform? Where do I start? What's the first thing I have to do? Yeah, I have to get x of t. Now I gave you what x of t looks like, and I guess I called it f here, and they call it x of t. All right, x of t. What would that be? I don't have to get all of x of t. That would be a very complicated thing to define. I need to define it over one period. Okay, I can do it over any period I want. Period I'm going to do it from is from 0 to capital T. All right, so help me out. From 0 to capital T, how am I going to do this? What's that? Split it up. Yeah, so what's the first? Yep, so it's 1 and -1. So this is from 0 to t over 2. And then this guy would be from t over 2 to t, like that. All right. So that's our function. So now then I got to compute my alpha n. So alpha n equals that integral. So how do I approach this? So I got to split that up, right? Because I can't put both of those x of t's under the same integrand, right? So how do I approach it? Alpha n is 1 over t times what? Integral to 0 to t over 2. Yeah, so I do the first part of it. 0 to t over 2 times 1, right? Well, I don't need to put the 1 there. I'll just say times e to the negative j n omega naught t dt. Okay. And then that's not all of it, is it? Isn't there more? Plus 1 over t times what? Integral, yeah, t over 2 to t of, in this case, -1. So what I'm going to do is I'm going to put a minus sign out in front. -1 e to the negative j n omega naught t dt. Very similar integrals, but not exactly the same. Okay. All right, now what? These are pretty easy integrals to do. All right, I will admit you're going to have some kind of uglier ones probably in the homework because you're going to have some that have integration by parts. They're not bad integration by parts, but they're integration by parts. In this case, what's my integral? Basically, I got an integral of e to the at dt. What's integral e to the at dt? 1 over a e to the at. Don't ever tell me it was, you know, some people will say, well, it's a times e to the at, and I'll say that's wrong, and they'll say, well, I had a 50-50 chance, right? It's not a 50-50 chance. Okay, it's a 0-100 chance. Basically, either you know it or you don't. There's not many integrals that you should know. This is one of them. All right. 1 over a e to the at. Okay. So in this case, what do I get for this guy? Right? Alpha n equals, let's do the first integral. What's the first one work out to be? Well, 1 over t times what? What comes down here? What's the a? So I did this e to the at, integral of e. What's the a? Negative j n omega naught. Okay. All right. Like that. Okay. Times, all right, e to the negative j n omega naught t evaluated from 0 to t over 2, like that. Okay. And then what's different about the other integral? I'll put this minus sign up here. Perfectly fine for me to move the minus sign to the top, right? What's different about the other integral? Anything? Just the sign, right? So this minus sign in front is going to become a plus sign. So I'm going to say this is 1 over j n omega naught capital T e to the negative j n omega naught t over 2 to t, like that. Okay. This is a definite integral. I got limits and all that kind of stuff. Not the most exciting thing in the world. What's this guy going to evaluate to? Well, okay. Yeah, I gave myself. So my alpha n, looking at this expression here, skipped ahead. My alpha n is this. How do I simplify that? Let's just, again, I don't want to get too engrossed in this thing here, but I can simplify whenever I have, and this is going to happen a lot, whenever I have omega naught's in terms of capital T, isn't it? How does omega naught relate to capital T? 2 pi over T. 2 pi over T. So that simplifies this term here, this term here, this term here, and this term here. All right. So I turn this guy into, if I plug that in, my alpha n becomes -1 over j n omega naught is 2 pi over t times t. Okay. Times, let's see. So I'm evaluating this guy. E to the negative j n omega naught from t over 2 to 0. How do I write that? How do I evaluate this term right here from t over 2 to 0? Yeah, and then plug in t over 2 into the t, and then plug in 0 to the t. So when I plug in 0 for the t, what happens to that exponential? What's it become? 1. Okay, so this guy becomes e to the negative j n omega naught. So that's 2 pi over capital T times t over 2, like that, minus 1. Okay, and you can go, you want to see the details on that, you can go back to look at the connection between those slides. The other one is going to work out to be plus j n omega naught capital T 2 pi over T. I don't want to get too bogged down in just deriving stuff. I don't like doing that. This becomes e to the negative j n omega naught 2 pi over t minus e to the negative j n omega naught t over 2. I don't have enough space to write that all out like that. Okay. You go through and you try to simplify this thing a little bit. You end up being able to simplify this quite a bit. You can actually simplify it more than I do, right? It simplifies down simply to 1 over j n pi times 1 minus e to the negative j n pi, like that. All right. I'll let you, those of you who are abundantly curious about the simplification, can do that at home. Okay. All right. We'll spend another 5 minutes simplifying it down, but it's fairly straightforward to do that. You could actually simplify that even further. If you went through and you actually plugged in, what you would find here is if you plugged in, if I plugged in an even number for n, right? If I plugged in an even number for n, what would I find? If n was equal to 0, what does this guy become? What does e to the negative j n pi become? Yeah, if I plug in n equal to 0, this guy would become 1. So 1 minus 1 is 0. That makes sense because alpha 0 is what term? What frequency? What term is that guy? Alpha 0. DC. Does this have a DC term? No. This guy doesn't have an average value. His average value is 0. So that's a good thing. If I plugged in n equal to 2, I would find that this becomes 0. If I plugged in n equal to 4, I'd find this becomes 0. If I plug in n equals 6, I'd find it becomes equal to 0. This guy only has odd harmonics. I said that at the very beginning when I started Fourier series. If you plug in even numbers and odd numbers, you'll see that it matches exactly what I said it was supposed to do. All right. I don't simplify it any further than this. This is what I would plug into MATLAB. Okay. Now, what I said is, if I want to get to the Fourier transform, I got 3 steps. First step is I got to get those Fourier series coefficients. Okay, we're done with that. We got the Fourier series coefficients. We got our alpha n. Next step is to map those to frequencies. Third step is to figure out then the x of omega and get the graphs. Okay, so all right, how do I map these to frequencies? All right, I want to map these to frequencies. So let's say I'm going to do it this way. So I got n values, and then I've got omega values. And let's assume, ideally, how many harmonics are in this waveform? How many e to the j omega t's are in this waveform? Infinite, right? That's impossible. I can't put that in a map. I can't plot that. My brain can't fathom that. Let's say I'm going to do n equal to 3. All right. At what frequencies do I have information in this guy? So what values of n? Let's start it that way. At what values of n do I have? Well, yeah, so I'm going to end up having stuff here at, if I look at this carefully, this guy is going to have stuff. So again, if you circle this out, what you'll find is that this guy is alpha n is equal to 0 for the n even. And then it's equal to something else for n equal to an odd number. Okay. So this guy, so if I say n equal to 3, I'm going to have something technically for n equal to -3, -2, -1, 0, 1, 2, and 3. All right. Now, again, what I just said was for the even ones, it's 0. There's not going to be anything there. But just in theory, I can have that many. That's how many harmonics exist. If I say n equal to 3, there's harmonics from -3 to 3. Okay. So what frequencies do those correspond to? What frequencies do they correspond to in terms of omega naught? Omega naught is my what's the name for omega naught? It's got a special name, right? What's the name of it? Fundamental, right? So I would say, so what frequency do I have for when n equals -3? What's the formula for that? Be what? -3 times omega naught, right? This guy would be -2 omega naught. I can get a number for that, but I like keeping it general, right? So this is negative omega naught. This is omega naught. This is 2 omega naught. And this is 3 omega naught. And then I've got alpha n's for each of those, right? So mapping my alpha n's to those, my alpha n, this would be my alpha -3. This would be my alpha -2. This guy would be my alpha -1. This guy would be my alpha 1. This would be my alpha 2 and my alpha 3. Now I left out the 0 term. What frequency do I have when n equal to 0? What's that? Yeah, DC is our term for it, right? DC is their average value. So I call this DC. All right. And this guy gets my alpha 0. All right. So I map what I'm doing. It's a very simple process. I say, what frequency do those correspond to? All right. Now what I want to do is I want to, well, I wanted to copy and paste that over there. I want to get that into my x of omega. My x of omega, this is the formula here that I put in. Okay. And so I said this is -3 omega naught, -2 omega naught, negative omega naught, 0, 2 omega naught, 3 omega naught. And so I said, I'm just going to put in for these ones that these terms, these alphas are zeros. These ones I don't want to go through the details like putting numbers in those. I want MATLAB to do that for me. All right, so I get those. So alpha -3, alpha -1, alpha 1, and alpha 3 are the non-zero guys. So if this is my formula for x of omega, what do I have for x of omega at each of these? Right. So alpha 1 here, or let's start at alpha -3. What would I get in my x of omega for alpha -3? What do I get for this term? So again, what I'm doing is I'm expressing the fact that at -3 omega naught, there is information in this signal. Okay, so how would I put that into this formula right here? It's an impulse, right? So what would I write out for alpha -3 or n equal -3? What would I write out there? So I get straight from this formula, right? It'd be alpha -3 times what? Alpha -3 times what? So it's that impulse, right? Delta of what? Omega plus 3 omega naught. Because that impulse has to be shifted over to n or to omega equal to -3 omega naught. All right, this guy would be alpha -1 times delta of what? Omega, what would I put for this? Plus 2 omega naught. All right, this guy would be alpha 1 times delta of omega -2 omega naught. This guy over here would be alpha 3 delta of omega minus, what did I say? Oh, I said, oops. It's plus omega naught minus omega naught. And this guy is -3 omega naught. And technically I said these guys, in general, they're there, but they're equal to 0 for this guy. So this is what the Fourier transform is. The Fourier transform, this guy is now a complex function of frequency, right? This guy is a complex function of frequency. And what's the meaning of that? What's that mean if I want to actually graph it? Right? I can plot a function by just having, whatever the output value on the y-axis and the input value on the x-axis. Can't do that here, can I? What do I have to do here if it's a complex function? Got to do the magnitude on one graph, angle on another graph, right? So this guy becomes two graphs. So in the context then of what you guys have in your homework, right? What you guys end up doing is you end up making what those graphs look like. This is what it would look like. If you go through that map where I had alpha n equals 1 over j n pi. What is it? 1 over j n pi. 1 over j n pi times 1 minus e to the negative j n. Oh boy. What did I say it was? Negative j n pi, like that. If I have that, okay, and what I have here, then my x of omega would be, I basically plug those in for all possible values of n, alpha n delta of omega minus n omega naught. Plug those in and make the two graphs. I put the magnitude of it and I put the angle of it. Now check that for a second. Why is this? See if you can justify it. So for n equal 1, I've got an impulse here at omega naught, and I said the angle is negative 90. Does that look right? Right? If I plugged in n equal to 1, what would I get here? If I plug in n equal to 1, I would get alpha n equals 1 over j n pi, where n would be 1. So alpha 1, 1 over j pi. And what do I get for this? 1 minus e to the negative j n pi. If n was equal to 1, what would that be? So e to the negative pi is negative 1. So this guy would become 2 over j pi like that. 2 over j pi like that. Okay. So I said the angle of that's negative 90. How can I tell the angle of that's negative 90? Yeah, this guy is the same as 2 over pi times negative j. Right? J in the denominator. So the way I can see that is I say this is an e to the j 90. Right? I think about that, e to the, so e to the j 90 is always, so where is j? If I have j, it points straight up, right? In the complex plane. So that guy means the bottom's got an angle of 90. So that means that this is e to the negative j 90. Right? That was my way to make that conversion. So it's got a negative 90 and it's got a magnitude. If you look at what happens to the magnitudes as n gets higher, well, they decrease because there's this 1 over n in the denominator there. Okay, so these guys are going to get smaller and smaller. So the fact they get smaller and smaller, what does that kind of mean? Well, that sort of means that the higher order harmonics, as n gets bigger and bigger, they don't mean as much. Right? The one that matters the most is probably this guy. Right? And then third harmonic matters a lot too. Right? But if I tried to get to n equal to negative 10 billion and 10 billion, they don't really matter that much. Their amplitudes are pretty tiny. Right? I don't need to capture all that stuff to make a square wave. So we'll think about that in some more detail next time. But that's an important point. All right. So how to code this? So here's an example, right? If I wanted to create that, so I think problems. I guess it's problem 3, 3, 4 on the homework, right? And 5, I guess, to some extent too. So 3, 4, and 5, I'm asking you to do Fourier transform. So how do I do that? So first thing I got to do, the very first step is I got to build the alpha vector. So when I said build the alpha vector as before, this is, so if you do problems 1 and 2, and at the very end of homework 7, I asked you the last 2 problems on homework 7, I asked you to plot the Fourier series, or so basically to plot X and to have your alpha value vectors and your B vectors and your A vectors, all that stuff. Do the same thing here, right? So what am I doing? I create an empty alpha vector, and then I create an n vector. And notice my n vector goes from, in this case, I'm doing this for 9 harmonics. So I start at -9, and I go to 9, okay? And then I loop through that vector, right? And then what am I doing? Every time I go through here, I'm adding in a new value to I'm appending, just like I did last time, right? talked about this last week. I'm concatenating a value, and notice I put this intermediate step in here that made it so that the math was a little bit easier for me to look at, right? What is this? What is this guy here? I probably didn't need to do this, but I did it for n equal to 0. I put a 0 in there. Technically, I probably didn't need that, right? But I always, as a matter of habit, always treat the DC term differently, right? Because technically the DC term is the average value of the waveform. And that can sometimes get messy. If I don't want to say anything more about that, I'll just confuse you. All right, I did the DC term separately. Okay. So once I've done this, I've got this, the output of this code is my alpha n vector. This is my Fourier series coefficients. Fourier coefficients. All right. Now, in the homework, what I'm expecting that you're doing, just to be clear, is I'm expecting that you're doing the integral. You got a formula and you got a for loop to populate that. Okay. Using whatever formula you derive by hand. All right. Now, the last step is if I want to look at the Fourier transform, here's what I do. Okay. Again, I had this in the code last time, but you guys can see it here again. So I create a omega vector. Now let's look at this omega vector. Omega starts at negative n times omega naught, increases in steps of omega naught, and ends at n times omega naught. So what's that? What's my omega vector if I looked at it? What's the omega vector going to have in it? It's going to be a row vector. And what's the first entry going to be? I said n equals 9. So what's the first entry going to be? Yeah, negative 9 omega naught. What's the second entry going to be? Yeah, negative 8 omega naught. And it's going to continue like that all the way up to 9 times omega naught. So notice I'm going to have one thing that may be useful to you. If in this case, if I'm doing 9 harmonics, this guy is going to have 2n plus 1 entries, right? 2n plus 1. Where did I get this number? So if n is the number of harmonics, I'm saying this guy has 2n plus 1. Where the heck did I get the 2n plus 1 from? Yeah, so the 2n comes from the fact that there's a 1 and a minus 1. There's a term of the positive frequency and negative frequency. So I always have 2 times for every sine wave, and then there's the DC term. So that's the plus 1. Because the DC term, there is no negative 0, right? So I had 2n plus 1 terms. So then what I did was I didn't have to do it this way. I could have just defined, I created a magnitude vector and I created an angle vector. Okay. And what I did here was again, something I talked about last time, I used this subplot thing. Okay. And I create, subplot makes 2 plots on top of each other. So one on, basically it's going to make a plot that looks like this. One on the top, one on the bottom. This guy here I called subplot 2, 1, 1. And this guy is subplot 2, 1, 2. So it's basically saying I got 2 rows of graphs, 1 column. This is the first one. This is the second one. Don't know why they decided to do it this way, but they did. Okay. All right. That's about all you're going to need to know about it. All right. You're not going to have to make a lot of subplots, but notice what I did here. So the other thing I introduced last time is I used this thing called stem. Right. What did I say stem did? That's my plot. Normally you say plot, right? You would say plot of omega magnitude. What the heck is stem? What did I say was the difference between stem and plot? Yeah, stem basically plots what amounts to an impulse. It plots a little stick with a ball on top of it. So it's a stem basically. So there's the point here, and then there's a stem that goes with it, okay? To me, this is how you can express impulses. And what I can see is that I've got impulses at the different spots, all right? And then everything else is 0 in between, all right? If I did, what would the graph look like if I had put plot? Well, how would the graph have been different if I did plot instead of stem? It would connect the points. So basically it would say, well, it goes like this to this, to this, to this, to this, to this, to this, to this. It would look like that. That is not what this thing looks like, right? In other words, that implies that the value between this point and this point is somewhere halfway in between them. That's not right. I know that it's 0. So I did the stem command instead. All right, so on the top graph, what I have is the magnitude. And on the bottom graph, I have the angle. All right, so I'm plotting the magnitude and the angle. Now, the one thing that is a little bit, shall I say, it's a little bit weird here, is it did give me an angle here at the negative, or sorry, like n equal to 2. This guy here is n equal to 2. This guy here is n equal to 4. This guy here is n equal to 6. It's giving me angles of like 180 degrees, which is a little bit weird, but it's numeric, right? So what does it mean to say at n equal to 2, this guy's got an angle of 180 degrees, but does that angle matter? No, because the coefficient is 0. It's basically saying I got 0 with an angle of 180 degrees. 0 doesn't have an angle. Right? What does that mean? That means that probably if I looked at the number, and this is the stuff when you guys complain to me like, oh, I can't get my answers in. Usually it's the first couple of people. Usually what's going on is most likely it's not 0. If I looked at the alpha value in MATLAB, you'd probably see that it's like 10 to the minus 15th plus j times 10 to the minus 16th or something like that. And so MATLAB's going to think that has an angle. Right, but that is basically 0. That's what's going on here, is some sort of numeric goofiness. Now it didn't happen for 0 because I physically hard coded a 0 in for that one. That's why I don't get the numeric weirdness. All right, I don't want to say much more on that because that's going to confuse too many of you. All right. The basic thing's not that hard to get through your head. All right, this is really a straightforward process. It's sort of these 3 steps. And at first it may look to you like, well, what the heck is he doing? So he taught us this Fourier series thing. Now Fourier transform. They're related to each other. The Fourier transform can be applied anytime I've got any waveform, whether it's periodic or aperiodic, right? That's where it gets really useful. Now, the thing is, there's one other step. What would I do with what's useful for me for a graph like this? All right, why is this useful? This becomes useful if I have a square wave and I can turn it into the frequency domain. This graph is useful for me for a couple of reasons. One of them is if I want to build what's called a filter. So in project 1, you build filters, right? So in this case, I want to talk about filters. Maybe I guess what I also wanted to talk about was when I see these waveforms, I can look at this and I can recognize, I should be able to recognize that this term and this term here correspond to a particular time domain waveform, right? These, and I should say their angles do as well, right? So if I looked at this, it turns out these guys right here, this is about 0.65, that magnitude. So I can say that this guy has a fundamental x1 of t. How would I use this information, this graph, to get back to what the actual time domain waveform is? How would I do that from this graph? Well, let's bear in mind what this graph is. This graph is x of omega is equal to alpha 0 plus alpha 1 e to the j omega naught t plus alpha minus 1 e to the negative j omega naught t plus a bunch of other stuff. So you use, sorry. This guy would be impulses. How would I use this? How would I use this to go back to an actual time domain waveform? I know I asked you this on the homework. If I wanted to plot the first harmonic, the fundamental term, how would I use this information? Yeah, so I would basically look at this and I would say, well, let me take the alpha 1 term and say that's e to the j omega naught t plus alpha minus 1 e to the minus j omega naught t. And that should equal to what? Well, it'd be 2 times alpha, magnitude of alpha 1, cosine omega naught t plus whatever the angle of alpha 1 is, like that. That would be the first harmonic term. And what I did, so this basically is my first harmonic. This one here is my third harmonic. And this is what? What's the yellow waveform? It's the sum, right? So, and if I kept adding harmonics in, that guy would get, the combination of them would look more and more and more like a square wave, okay? That's our basic idea. The thing I want to explore a little bit is where would I use this stuff? Okay, so here's the example I kind of want to end on today, and we'll get into thinking about this a little bit more on Wednesday. Okay, so what I have here is a simple little goofy picture of an Arduino and a motor. So a simple robotics sort of problem, right? So what I've got is an Arduino microcontroller, right, that is connected to, some of you guys may have seen this if you've messed with it at all. This would be a, I don't know, a motor shield, I think is what they call this, right? This guy is a motor driver. All a motor driver is, fundamentally, is something that takes a little weeny square wave that comes out of a microcontroller and basically beefs it up, which is a very technical term, to beef it up, basically meaning that more current can go into the motor, more amps, okay? I need amps for motors. Microcontrollers can't give me amps. Okay, so looking at this picture right here, so you guys may have heard this term before here. What I have here is a PWM wave. So this waveform would, so the microcontroller generates this nice little waveform. All right, it's a simple square wave. And then I pass it into this motor driver, which makes a voltage that I apply to the motor that looks like this. Now in robotics, in this case, I got a DC motor. Is this a DC waveform right here? Is that a DC waveform? What would make it a DC waveform? What would it have to look like? Super flat, right? Is that flat? No, right? It's most likely, in a lot of cases, it says 12 volt DC motor. So this might be 12 and then 0. So it's 12, 0, 12, 0, 12, 0, 12, 0. That's not DC, right? Now, what would be the best way to, what would be this, if I wanted to make a DC motor speed up or slow down? All right, you guys don't know much about motors, but what do you probably know enough to say, what would be the simplest way to make a DC motor go faster? What do you think you would do to make a DC motor go faster? Well, you know enough about this. I would basically apply more volts to it. If it was a DC motor, if I didn't know any better, when I was microcontrollers weren't as simple to use, and I'd program and go through a bunch of stuff, right? So if I would take a power supply and I would turn it from 0 volts to 12 volts, and I'd turn it from 0 volts to 12 volts, the motor would go faster, right? So if I wanted to make that, what I would probably do is I'd have a 12 volt battery and a potentiometer. And then my motor, I'm not going to get to a full circuit model for that. Motor, we'll call it a big circle with an M. Okay. That's my motor for that thing. And if I took that potentiometer and I turned it, right, the voltage that I got here would get bigger. All right. And that would work. That would control the DC motor. All right. What's bad about this? This fundamentally and is the way that motors work. If you went back to a long time ago, back to the early days of subway cars or something like that, there was a guy with a potentiometer that would control the speed of the subway car. All right. What's bad about this approach to control speed? It works. It's very simple. Works great. What's bad about this as a way to control speed? If I have a resistor here, right? What's going to happen? What happens if I have a resistor and I have current flowing through a resistor? It dissipates heat, right? And if I want to go really slow, it's going to dissipate a lot of heat. All right. So this resistor, this works quite well. All right, it makes a variable supply for me, but it's not a very efficient way to do it. All right, so there's an almost 100% efficient way to do it, which is the picture that I've got here. Okay. Now I'm a DC motor. I like a DC voltage. What I have here is I'm actually applying an AC waveform. Now this waveform has a period capital T. And then I have this thing D that I call the duty ratio. So D is some fraction between 0 and 1. Okay. Now, if I think about this, what I can change is I can change that duty ratio D. So in my microcontroller, I would change that fraction. So I change the fraction of the period that this guy is high. Okay. So let's think about what that means. How can I represent, let's call this guy, I don't know, V motor. All right. This is V motor. Okay. How can I think of V motor? If I want to think about this guy from a design perspective here, V motor is a what? It's periodic, which means that I can express it how? Sum of sine waves. So V motor is basically some waveform that goes from negative infinity to infinity, alpha n e to the j n omega naught t. Okay, so I can express it that way. And this guy's going to have a whole bunch of stuff in it. All right, now think about it like this. Alpha, what's alpha 0? That's the what term? What frequency does alpha 0 correspond to? The DC term. And the DC term is always the what of the waveform? The average. So if I do this 1 over t, 0 to t of this waveform, Vm of t dt. Okay. If I go through and do that math, what I'm going to find out is if this waveform has if the peak value here is 12 volts, I'm going to find out that this is D times 12. Right? 12 times D. So that means that my duty ratio is 1, I'm applying 12 volts at DC. And if D is equal to 0, I'm applying 0 volts. If D is 0.5, I'm applying 6 volts. So what this guy is saying is by making this, by doing this approach, Vm of t, the motor voltage, is equal to some DC term, 12D, plus some sum of sine waves. So something at, you know, cosine of omega naught t, plus something at cosine of 3 omega naught t, blah, 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 blah. That means if I applied this voltage to the motor, what should the motor do? If I told you this was the motor, so some of you have done this before. If you applied that voltage to a motor, what's the motor do? It just spins constantly, right? That's not what it should do, right? Shouldn't the motor start and stop and start and stop and start and stop and start and stop? Shouldn't it do that? Why does it spin constant? Why does it spin constant? Because the motor is filtering these guys out. The motor's not responding to to those things. So basically what I'm saying is I think about ways to do this. If I can represent that waveform in terms of this Fourier transform, and I say, well, I'm going to make sure that the motor is set up. So if I overlaid the motor's, what I'm going to call the motor's Fourier transform on top of this thing, the motor is going to make sure to have a 0 Fourier transform out basically everywhere where these harmonics exist. All right, and we're gonna explore that concept more on Wednesday. But basically, what this does is it allows me to do a design problem. It lets me to say, all right, well, I want to drive a motor. Okay, so I want to think about the waveform I'm driving the motor with as this Fourier series, and then I want to say, okay, well, how's the motor going to respond to each of those frequencies? As long as I set everything up right, the motor is not going to respond to these harmonics, but it will respond to the DC piece. All right, and that's where we can begin to use this. Basically, is where we can think about how to use it from a design perspective. And that's what we'll dive into more on Wednesday. Okay, and then we'll talk about that through next week for the project. Okay, all right, that's it.